Here's that last problem that we didn't quite get to in class. And I've taken the liberty of outlining it and pulling the information out um, ahead of time, and now we can go ahead and solve the problem. But it says water under 4 atms of pressure, so that's right here, 400,000 pascals, that's 4 atms of pressure, is traveling in pipe with a diameter of 6 centimeters, right? So here's the cross-sectional area of that pipe, pi times radius squared, and the water has a flow rate of 3 times 10 to the negative 4 cubic meters per second. There's the volume per time. And then it flows into a smaller pipe of a diameter equal to 3 centimeters, which is right here. And that pipe up top will have a cross-sectional area of pi times r squared, is this number here. And it also goes up 4 meters in height, so I've labeled y1 as 0 and y2 as 4, right? And so I'm going to go ahead and I need to solve for pressure too. That's the question. What's the pressure up top in that pipe? Well, the pressure went down for 2 reasons, right? So first and foremost, I'm expecting a number under this one, right? Because the pressure is going to go down for 2 reasons. The pressure is going to go down because there's less water depth, it's up higher, but the pressure is also going to go down because it's speeding up, right? So that's what our equation can help us find. The first thing we're going to need to know are the velocities, right? So we're going to have to go after the equation of continuity first and say that, how about A1 V1 equals volume per time? So the velocity down low, V1, is going to be V per T, which we have a number for, times 1 over area. Okay? So V1 will be volume per time, which is 3 times 10 to the negative 4. Those are cubic meters per second. There's the V per T right there. Times 1 divided by the area, which I've already figured out here, is 2.83 times 10 to the negative 3. 2.83 times 10 to the negative 3, and those are square meters. Okay. So that'll be the velocity down here, and I'm going to write it down. Maybe I'll write the V's up here. V1 will be equal to something. Okay, so the math is going to be pretty straightforward because numerator times 1 is our value, 3e4, negative 4, and divided by this number here. So I just have to do 3 exponent negative 4 times 1, so it is 3 negative 4, divided by 2.83 negative 3. 2.83 exponent negative 3 is 0.106. 0.106 meters per second is V1. 0.106 meters per second. It's not going very fast. It's going, 10 centimeters a second. Slow flow. Okay, now we can do the same thing again to get V2, but if you're tuned in, you know that A1 V1 equals A2 V2. That is to say, the ratio of the velocities is the inverse of the ratio of the areas, and this pipe is half the diameter of that pipe, so it must be 1/4 of the area, so it must be going 4 times faster than that, right? So we can do this again, and but we're going to get 0.42 again, or we're going to get 0.4, something like that, right? So V2 is going to be 4 times V1 because A1 is 4 times bigger than A2. And if you don't believe me, just work it out the same way I just did this one. But it's going to be 0.106 times 4. So 0.106 times 4 is about 0.424. 0.424 meters per second. Right? It's going to speed up by a factor of 4 because the area went down by a factor of 4, which is to say the radius went down by a factor of 2. Okay, so there's my 2 V's, V1 and V2. And that's 0.424 meters per second. And then I just pull out the Bernoulli's equation, right? Which is P1 plus rho GY1 plus 1/2 of rho V1 squared is P2 plus rho GY2 plus 1/2 of rho V2 squared. Okay? And up here, I've taken y1 to be 0 meters. So this will be 0, 0. And I am after pressure 2. Right, so I'm going to just subtract these two items to the other side. I'll have P2. So P2 is going to equal 1/2, P2, I'm subtracting everything over. Yeah, so P2 will be P1 plus 1/2 rho V1 squared minus rho GY2 minus, that's a 2, sorry, minus 1/2 rho V2 squared, 1/2 rho velocity 2 squared. And I'm ready to solve. I've got everything I need here, right? So it's water, so I know the density. I didn't write it, but the density of water is 1,000 kgs per cubic meter. I'll make sure that's written down. And I'll go ahead and just solve this out. So P2 equals 4 ATMs, so that's 400,000 pascals, plus 1/2 of rho, I'm just going to write 500. 1/2 of 1,000 is 500 kgs per cubic meter. 1/2 rho. V1 squared, that's 0.106 squared, 0.106 meters a second. That gets squared. And I minus rho GY2 minus 1,000 times G. I'm just going to call that 10,000. I guess the units are a little bit funky here. I'm just going to leave them out. 10,000, bad form, but I'm doing it. 10,000, and Y2 is what, 4 meters, minus 1/2 rho V2 squared. So again, minus 1/2 of rho, that's 500. 1/2 of 1,000 is 500 kgs per cubic meter. And V2 squared is 0.424 squared. 0.424 meters a second squared. Now it's just math, right? Now it's just math. Let's see what we get here. So 400,000 plus the quantity 500 times 0.106 squared. 500 times 0.106 squared. Right? Close them out. Minus the quantity, minus 40,000. Minus 10,000 times 4 is 40,000. Minus 40,000. Minus the quantity of 500 times 0.424 squared. And this needs to be less than 400,000 for reasons I mentioned a minute ago. And when I hit it, I get 359,916. P2 is 359,916, 359,916 pascals. Lower indeed for 2 reasons. And I'd probably report this as P2, and out of space here, that's okay. P2 equals 3.6 times 10 to the 5th pascals. And that's how you do it, right? So it just takes practice. It's a big, long equation, but it's relatively straightforward to deal with as long as you are clear about, make your lists and pull out what you know and strike things to 0 when you can, and you'll get it. So now go get problem set 2. All right, people. See you soon. Bye.